हेलो दोस्तों, वेलकम टू पायोज एकेडमी।
Payos. Learn the smarter way.
Alright, let's start with interview question on line sizing. Why do we actually need line sizing in a process plant? Why can't we just pick a standard pipe size and move on?
Line sizing is required because every process is unique, even if it looks similar on paper. Flow rate, fluid properties, operating pressure, temperature, allowable pressure drop, and future flexibility all change from project to project. If we blindly copy line sizes from old projects, we risk either undersizing or oversizing the line. In my experience, line sizing is not just about hydraulics. It directly impacts pump head, control wall authority, operating cost, and long term reliability. Proper line sizing ensures that the system operates within acceptable velocity and pressure drop limits, avoids erosion, noise, vibration, and also keeps capex and opex optimized. That's why line sizing is a fundamental process design activity and not something that should be copied.
In your experience, what problems have you seen in plants due to improper line sizing?
I have seen problems related to both undersized lines as well as oversized lines. In undersized lines, we face high pressure drops, pumps running at higher heads than expected, control walls staying almost fully open, and frequent complaints from operations that not achieving required flow. In some cases, erosion and noise were serious issues, especially in high velocity liquids and steam lines. On the other hand, oversized lines create low velocity issues. I have seen liquid lines where solids settled, leading to choking and maintenance problems. Oversized vapor lines causes poor control because the control wall becomes too small relative to the line, resulting in hunting and unstable loops. So, improper line sizing almost always shows up later as operational headaches.
Now tell me, when we talk about pipe schedule, what exactly does schedule mean? And where does it become important from a process engineer's point of view?
Pipe schedule defines the wall thickness of pipe for given nominal diameter. From a process perspective, line sizing gives me nominal pipe size based on the hydraulics, but schedule selection comes from mechanical design based on design pressure, temperature, corrosion allowance, and material strength. However, schedule indirectly affects hydraulics as well because higher schedules reduces internal diameter slightly, which increases velocity and pressure drop. So, while I don't select schedule during line sizing, I always remain aware that internal diameter used in calculation should match the expected schedule. Coordination between process and piping is important during selection of pipe schedule.
When you receive a new line sizing task, what key inputs do you collect before starting calculations?
Before starting any calculation, I collect flow rate, minimum, normal, and maximum, fluid properties like density and viscosity, operating and design pressure and temperature, line routing information such as approximate length and elevation changes, and any special constraints like erosion limits or noise concerns. I also check whether the line is in pump suction, pump discharge, gravity flow, or control wall downstream because the allowable pressure drop criteria will change accordingly. Without these inputs, line sizing becomes guesswork. So I always clarify them upfront.
How does line sizing philosophy differ for liquid service compared to gas or vapor service?
For liquid service, line sizing is usually governed by velocity limits and pressure drop per unit length. Liquids are incompressible, so density remains almost constant and elevation change plays a major role. We mainly focus on avoiding erosion, noise, and excessive friction losses. For gas or vapor service, compressibility becomes important. Density changes with pressure and temperature, so velocity increases significantly along the line. Gas line sizing is often governed by velocity limits, especially Mach number and allowable pressure drop to ensure downstream equipment receives sufficient pressure. Noise and vibration are also more critical in gas lines compared to liquids.
Can you walk me through your typical step by step procedure for sizing a process line?
First, I identify the service and confirm whether it's liquid, gas, or steam. Then, I select an initial line size based on recommended velocity ranges. After that, I calculate pressure drop using standard correlations, including frictional losses and losses due to fittings and walls. I then check whether the calculated pressure drop is within allowable limits. If it's too high, I increase the line size. If it's too low and velocity is very small, I reassess for possible oversizing. Finally, I validate the selected size against mechanical and layout constraints before freezing it.
What is the difference between static pressure loss and dynamic pressure loss? And where does each one become important?
Static pressure loss is related to elevation change. For example, when a liquid flows upward, pressure is consumed to overcome gravity, and when it flows downward, pressure is gained. Static loss is independent of flow velocity. Dynamic pressure loss, on the other hand, is due to friction and turbulence as the fluid flows through pipes, fittings, and walls. Dynamic pressure loss depends on velocity, pipe roughness, and flow regime. In long horizontal lines, dynamic loss dominates, while in vertical lines, static loss becomes equally or more important.
What do you mean by equivalent length? And how do fittings and valves affect line sizing calculations?
Equivalent length is a way to represent the pressure loss caused by fittings and walls in terms of equivalent straight pipe length. Instead of calculating each fitting loss separately, we convert elbows, tees, walls, and reducers into equivalent lengths and add them to straight pipe length. This simplifies calculations and ensures we don't underestimate pressure drop. In complex piping systems with many fittings, ignoring equivalent length can lead to significant errors in line sizing.
Why do we convert fittings and valves into equivalent length instead of handling them separately?
In real piping systems, fittings and walls can contribute a significant portion of total pressure drop, especially in short lines or congested layouts. Handling each fitting separately using loss coefficient is accurate, but during early design and quick checks, converting them into equivalent length is more practical. Equivalent length allows me to quickly visualize the hydraulic impact of piping layout decisions. For example, if line looks shorter on paper but has many elbows and control walls, the equivalent length can become much larger hydraulically. This approach also helps during discussion with piping and layout teams because we can easily explain why additional bends or rerouting will increase pressure drop.
From a piping design perspective, what is the difference between a bend and an elbow? And how does it affect hydraulics?
An elbow is a standard forged fitting, usually 90° or 45° with a relatively short radius. A bend is found by bending the pipe itself and typically has larger radius. Hydraulically, bends causes less pressure drop than elbows because the flow direction changes more smoothly. In high velocity or large diameter lines, I always prefer bends over elbows to reduce pressure loss, erosion, and noise. This becomes especially important in pump suction lines or compressor suction lines where flow disturbances can affect equipment performance.
What is the difference between pipe and tube? And why are pipes preferred in most process plants?
Pipes are sized by nominal diameter and schedule, and they are designed to handle pressure. Tubes are sized by outside diameter and wall thickness and are generally used for heat exchangers or instrumentation where precision is required. In process plants, pipes are preferred because they are robust, standardized, easier to fabricate, and suitable for high pressure and high temperature services. Tubes are more common inside heat exchangers or for small bore services, not for main process transfer lines.
What are spectacle blinds and spacers? And how do they impact line sizing or pressure drop considerations?
Spectacle blinds and spacers are isolation devices used to positively block flow during maintenance. A spectacle blind has two positions, blind and spacer, and is installed between flanges. From a line sizing perspective, they introduce additional thickness and minor disturbances in the line, but their pressure drop impact is usually negligible and not considered in calculations. However, their presence is important during layout and stress review, and I always ensure sufficient space is provided for their operation.
What velocity limits do you normally follow for liquid, gas, and steam lines? And why are these limits important?
For liquids, I typically follow velocities of around 1 to 3 meter per second depending on the service, with lower values for corrosive and erosive fluids. For gases, velocities are generally kept below 20 to 30 meter per second to control noise and pressure drop. For steam, velocity limits depends on pressure level but are generally in range of 15 to 30 meter per second, keeping erosion and noise in check. These limits are important because excessive velocity leads to erosion, vibration, noise, and higher pressure drop, while very low velocity causes settling, poor heat transfer, and control issues. Velocity is often first selection criteria in line sizing.
Apart from velocity limits, what pressure drop criteria do you apply for liquid and gas lines?
For liquid lines, I typically use pressure drop per unit length as a guideline, especially for long lines. The allowable pressure drop depends on whether the line is gravity flow, pump discharge, or suction. Pump suction lines have very tight limits to protect NPSH. For gas lines, pressure drop is often expressed as a percentage of operating pressure. Excessive pressure drop can affect downstream equipment and control valves. I always ensure enough margin is available for control and future debottlenecking.
How does line sizing directly impact pump sizing and compressor selection?
Line sizing directly affects frictional losses, which are a major component of pump head and compressor discharge pressure. If a line is undersized, the pump head increases, leading to higher power consumption and possibly a larger pump. Conversely, a well-sized line can significantly reduce energy consumption over the plant's lifetime. That's why line sizing decisions made during early design have a long-term impact on operating cost.
From a project cost point of view, how does correct line sizing help in optimizing capex and OPEX?
Correct line sizing strikes a balance between capital and operating cost. Oversized lines increases material, fabrication and support cost, while undersized lines increases power consumption and maintenance cost. By selecting the optimal line size, we avoid unnecessary material while ensuring efficient operation. In large projects, even one size change across multiple lines can have significant cost impact. So, line sizing is a key optimization tool.
If a line is oversized, what operational and control problems can occur?
Oversized lines lead to low velocities, which can cause liquid stagnation, solid settling, and poor mixing. From a control perspective, oversized lines often result in control walls being too small relative to the line, causing unstable control and hunting. I have also seen issues where oversized lines made startup difficult because the system response becomes very sluggish.
What issues do you expect if a line is undersized?
Undersized lines usually show problems very quickly in operation. High velocities lead to excessive pressure drop, erosion, noise, and vibration. Pumps and compressors end up operating at higher heads or discharge pressure than intended, which increases power consumption and shortens equipment life. From a control perspective, control valves remain almost fully open, leaving very little control margin. Operators often complain that they cannot achieve the required flow or that the system becomes unstable during load changes. In my experience, undersized lines almost always lead to repeated debottlenecking exercise later.
Let's take a practical case. A 100-meter horizontal 4-inch pipeline is carrying 50 cubic meters per hour of water at about 2 bar and 60 degrees Celsius. Now the routing changes to 60 meters horizontal and 40 meters vertical upward. What changes hydraulically?
In the original horizontal line, pressure drop is mainly due to friction. When the line is rerouted with a 40-meter vertical rise, static head becomes a major factor. Water will require additional pressure to overcome elevation, roughly equivalent to the hydrostatic head of 40 meters. This static loss is independent of flow rate. So, even at low flow, the system will experience that pressure requirement. Practically, this means the upstream pump must now generate additional head or the downstream pressure will drop. If this change is not considered during design, the pump may fail to deliver the required flow after routing modification.
Can the same line size be safely used for liquid and gas service? What changes hydraulically?
Using the same line size for liquids and gas service is generally not advisable without rechecking hydraulics. Liquids and gases behave very differently. For liquids, density is constant and pressure drop increases linearly with flow. For gases, density changes significantly with pressure and velocity can increase sharply. A line that is acceptable for liquid service may result in very high velocities, noise and pressure drop when used for gas. In practice, gas lines usually require larger diameters to keep velocities and Mach number within limits.
What happens if the number of bends and fittings increases in a line routing?
Every bend, elbow, and fittings add local resistance to flow. As the number of fittings increases, the equivalent length increases, which raises total pressure drop. In real projects, I have seen routing changes in lead design that significantly increased pressure drop and forced us to revise pump sizing or line diameter. That's why close coordination with piping and layout teams is critical. A hydraulically short line on paper can become hydraulically long in reality due to fittings.
In real projects, how do you balance hydraulic requirements with piping layout constraints?
It's always a compromise. Ideally, we want straight, short lines with gentle bends, but layout constraints like equipment spacing, accessibility, and safety often dictate routing. As a process engineer, I communicate critical lines clearly, like pump suction line or gravity flow lines, to the layout team. If compromises are unavoidable, I reassess hydraulics and update calculations rather than assuming things will work. Early involvement in layout reviews helps me to avoid late surprises.
Have you ever had to revise a line size after stress or layout review? What was the reason?
Yes, that happens quite often. One common reason is additional fittings or longer routings introduced during stress analysis. In one project, thermal expansion loops increased the line length significantly, which increased pressure drop beyond acceptable limits. In such cases, we either increase line size or revisit operating philosophy. It's good example of why line sizing is not one-time activity but an iterative process.
How do line sizing assumptions change for minimum, normal, and maximum flow conditions?
At minimum flow, I check that velocity is not too low to avoid settling or poor control. At normal flow, I ensure the line operates comfortably within velocity and pressure drop limits. At maximum flow, I check erosion, noise, and whether pressure drop remains acceptable. A good line size performs reasonably well across entire operating range, not just at one point.
What are the most common mistakes young process engineers make while doing line sizing?
The common mistake is relying on single flow case, usually normal flow. Another mistake is ignoring fittings and elevation changes. Some engineers also blindly follow velocity limits without understanding the service. In my experience, good line sizing comes from understanding the process intent, not just applying formulas. Asking the right questions upfront will avoid most of the mistakes.
Final question. If you inherit a running plant with unstable operation, what line sizing related red flags would you look for first?
I would first look for very high or very low velocities, whether control valves operating nearly full open or almost closed, frequent pump trips, and excessive noise or vibrations in the line. I would also check whether any routing changes were made during construction or debottlenecking without updating hydraulics. Many operational issues trace back to line sizing decisions that were made years earlier.
Alright, that gives me a good understanding of how you approach design. Thank you.
Thank you.
Payos. Learn the smarter way.